So I thought it would be fun to go ahead and implement matrix multiplication from scratch in Rust. I've been really kind of interested in matrix multiplication lately because I've gone down kind of this rabbit hole of all of the different algorithms to actually compute the product of two matrices. There's all sorts of really cool stuff out there. And matrix multiplication in general is super important, right? It's the backbone of effectively all of machine learning. And for all you see about, AI right now and generative AI in particular, it's all just matrix multiplication. There's really not much more going on than that. So I thought this would be a little cool project to do, to just kind of benchmark performance of if we implement this kind of naively in Rust using only the standard library, how fast can we make it go and how close do we get to hyper optimized tools like PyTorch. I'm in the process right now of actually learning Rust. I've been through all of the documentation, watched a couple like tutorial videos, but there comes a point when you're learning a new programming language where you actually have to jump into it and start building things. And that's kind of where I'm at now. So matrix multiplication is a really great project for learning a new programming language because it gets you exposure to so much of the language, right? You're going to get exposure to type checking, iterating through the rows and columns of the matrix, parallelizing the multiplication, object-oriented programming, implementing traits, types, methods, operator overloading, so just by doing this relatively simple thing, we're going to get exposure to just a tremendous amount of the Rust ecosystem. And that's going to be really helpful for understanding actually how the language works. So here we have our blank slate Rust package. The general API that I want to go for here is very similar to a NumPy or a PyTorch. So if you're familiar, you've probably seen things like this. Like if you were to create a tensor in PyTorch, you could do something like this, torch.tensor, and then pass in a list of integers, of floats, whatever, and this constructs a tensor object in memory. NumPy is very much the same way. And so this is kind of what I'm going for in Rust. There are Rust libraries like NDArray that kind of implements something close to this, but with the more Rust-like syntax. So kind of by the end of this video, we should be able to pretty much do something like this, where we can assign a tensor object based on a list and have this compile. This is the idea. So to start, the first thing that we need to actually do is define what our tensor object is going to be. And I'm going to call this thing a 1D tensor. This is where we're going to start. The idea is a 1D tensor is like a vector, right? And we know that matrices are collections of vectors. So 2D tensors are just collections of 1D tensors. And I think splitting up these objects in that way is just going to make implementation a lot easier for us and save us a lot of headaches. So tensors are comprised, right, of elements. And those elements are just what is in the tensor, right? And then it also has some dimension to it, right, which is going to be equal to your number of elements. It's nice to store dimension because it just allows you to very quickly access like the length of the tensor rather than having to count each time how many elements are in it. So the elements of the tensor, those are going to be, for right now, we're going to store them in a vector. And there's pros and cons to doing this. The pro is vectors in Rust are really, really flexible. So we can add elements to them at a later date. There's all sorts of methods that come along with them that are going to make them easy to manipulate. The con to that is that vectors are heap allocated. So if we want to get access to the contents of this vector, it's going to take us more time because we have to trace where on the heap this data lives and then return it. Arrays are stack allocated, and arrays will be faster, but for now we're just getting started, so let's do vector stuff. So this is going to be a vector. Now in Rust, we would like to be able to do something like this to specify that this vector is going to be either an unsigned 32-bit integer or a 32-bit float. Rust does not give you this type of type checking syntax, and largely that's just because of the way the Rust compiler works. So what we have to do instead is we have to basically say this vector is going to contain some generic type. We haven't defined the type yet. This is like a variable in a math formula where the variable can be pretty much anything. But we're going to say that this tensor consumes some generic type, which we're then going to place constraints on a little bit later. If you're really unfamiliar with Rust, this is going to look like, why are we doing this? But I'll make it much more clear in a little bit. For the dim, this is just going to be an integer, basically of any size. So this is our struct. So now that we have our struct, we can go ahead and we can actually start to create a new tensor. So let's call this here T2, which is going to be equal to our 1D tensor object. And in here, in the elements, let's just pass a list. I mean, I should say an array, because this is Rust. And remember that our struct is expecting a vector here. So we need to call the toVec method to convert this array into a vector. And then for the dimension, we know the dimension of this is equal to 3. Let's get rid of that. And then let's print out tensor dimension, and this is going to be equal to t2.dim. And if everything goes right, when we compile and run this Rust code, this will say tensor dimension of 3. Let's comment out that line, and then we have cargo run. Yeah, tensor dimension 3. We're looking good for right now. The next thing we need to do here is we need to actually implement the constructor for our tensor object so that we can get basically this really nice constructor syntax here. So to do this, let's implement the methods for our one-dimensional tensor. Now, because we're using this generic type t, which again can be anything, we haven't specified exactly what t is yet, but because our one-dimensional tensor takes that generic, the implement keyword also needs that generic as well. So let's create a new method, and we're going to call this method new. And this is going to consume an array, right, just like this. So we know that this is an array. The elements of that array are going to be of type T, just our generic placeholder thing for now until we say specifically what has to be in the array. And this array can be of any length. So we're going to use another generic here, which again, I'll show you, we're going to actually define this like really specifically, but for right now, let's just say that this array has a length of n, right? Arbitrary length. This is going to return back to us our 1D tensor. Okay. And here we can just construct the tensor, right? So elements is going to be equal to right, the input array. We're going to convert that to a vector, and that is our new elements. And then the dimension of this is just going to be equal to the length of the input array. So this is, you know, pretty clean, all things considered. Now, what we haven't done, right, is we haven't said what the length of this array can be. And we know that really we should be able to pass in any length. So what we can do is for the new function, we can define what this value of n is going to be. And we can say n is just going to be some constant. It's an integer of any size. And so this is how we're able to actually tell Rust, okay, this array can be of any length. It doesn't matter what it is. So that's kind of one hanging issue solved. The next thing to sort out is, all right, what is this generic t? Like, what is actually the constraint we're going to put on what is allowed to be contained within our tensor? Rust is really good at type checking if you're only expecting an input to a function to be a single type. So if it's you know, unsigned 32-bit integer, or if it's a 32-bit float, like Rust is really good at checking that. Rust is not great at when the input to a function could be one of two types or one of three types. Like, it's not super efficient at that, and it's just because of the way the compiler works. So instead, what Rust does is it checks the traits of the thing that you're passing to the function. So I'm not going to go over like what Rust traits are. I'm just going to kind of show how we use them, and then if you need to brush up on it, you can check the documentation. But the idea here is for our tensor, we're going to consume some generic type t, but t has to actually be able to implement some different traits. One of those traits is addition, right? Whatever the elements of the input array are, we have to be able to add them. The next thing that we need is we need multiplication, right? We need to be able to multiply the elements together. That's right. We're doing matrix multiplication here, so we got to be able to multiply. The last thing that we need is we need to be able to clone the contents of the array. So let me explain that one here after we do this. Clone. So the idea of cloning is we're basically going to duplicate the contents of our elements array, like down here in this example, right? So this array here, when this data gets passed to the constructor, when we call the toVector method, we're making a copy of that data someplace out in memory. And whatever the contents are of this array, we have to be able to copy them. They have to implement this clone trait. Now, there is a difference between copy and clone in Rust, but for now, we're just going to treat them as if they're the same thing, and that's close enough. So whatever this type t is, we're going to allow it as long as we can add it, we can multiply it, and we can clone it. And right now, those are our three constraints. Now that we have the generic type checking issue sorted, we pretty much have what we want. This constructor will kind of give us this interface down here that we wanted. Now, the only difference is that we called this tensor, but really we want it to be a 1D tensor. And so let's comment out this line down here, replace that. So when we compile and we now run our Rust code, we should get a tensor with a dimension of 3. All right, so we'll do a cargo run. And you can see the tensor dimension is 3. This is great. Let's try changing this. Let's expand it out to 4, 5. Let's run it again. And you can see the tensor dimension is 5. Really, really nice. The next thing to check is if we can create a tensor with floats. So if we delete everything in here and replace this with 1 and 2, this just dot means that we're going to treat them like floats. Let's try and compile this. It compiles and it runs. Very nice. What we don't want to be able to pass to a tensor is some object that isn't a number, right? So let's say strings. Let's try and pass some strings to our constructor and see what happens. Rust is going to yell at us for this. And the reason why is because of the trait constraints that we talked about earlier. You can see here, this first error says no implementation for the addition between two strings, right? Rust, in Python you can add strings, but in Rust, that's not the way that things work. Same thing down here for no implementation for the multiplication of two strings, right? That's not a defined trait, so we cannot pass that content to our tensor. This is how Rust handles like complex type checking. It's a little bit more verbose, but it does give you a lot of control over what to allow and what to not allow into your code base. So I just went ahead and cleaned up some of the syntax here, in particular the where clause in this implementation block. I just took a lot of the imports from the standard library and put them at the top of the file, and that just makes this a lot more easy to read, right? Because now we know that this generic type t implements addition, multiplication, and also the clone trait. I think this is a really good pass at you know, the API that we were after. Next time, probably we're going to implement some more methods, and we might take a stab at creating 2D tensors.